Researchers from the Harvard John A. Paulson School of Engineering and Applied Sciences (SEAS), in collaboration with researchers at McMaster University and University of Pittsburgh, have developed a new platform for all-optical computing, meaning computations done solely with beams of light. Now, before we start, make sure you hit the subscribe button, and if you already did, do click on the bell button so that you will not miss out any of our new videos. The future of computation is bright, literally. According to Amos Meeks, a graduate student at SEAS & Co. first author of the research, most computation right now uses hard materials such as metal wires, semiconductors and photodiodes to couple electronics to light. The idea behind all-optical computing is to remove those rigid components and control light with light. Imagine, for example, an entirely soft, circuitry-free robot driven by light from the sun. These platforms rely on so-called nonlinear materials that change their refractive index in response to the intensity of light. When light is shone through these materials, the refractive index in the path of the beam increases, generating its own, light-made waveguide. Currently, most nonlinear materials require high-powered lasers or are permanently changed by the transmission of light. Here, researchers developed a fundamentally new material that uses reversible swelling and contracting in a hydrogel under low laser power to change the refractive index. The hydrogel is composed of a polymer network that is swollen with water, like a sponge, and a small number of light-responsive molecules known as spiropyrin, which is similar to the molecule used to tint transition lenses. When light is shone through the gel, the area under the light contracts a small amount, concentrating the polymer and changing the refractive index. When the light is turned off, the gel returns to its original state. When multiple beams are shone through the material, they interact and affect each other, even at large distances. Beam A could inhibit beam B could inhibit beam A, both could cancel each other out or both could go through, creating an optical logic gate. According to Kalawi Chelvi Saravanamuttu, an associate professor of chemistry and chemical biology at McMaster & Co. senior author of the study, though the beams are separated, they still see each other and change as a result. We can imagine, in the long term, designing computing operations using this intelligent responsiveness. Co-author Derek Moram, a graduate student in Saravanamuttu's lab, said, "Not only can they design photoresponsive materials that reversibly switch their optical, chemical and physical properties in the presence of light, but they can use those changes to create channels of light, or self-trapped beams, that can guide and manipulate light." According to Joanna Eisenberg, the Amy Smith Berelson Professor of Materials Science at SEAS & Co. senior author of the study, materials science is changing. Self-regulated, adaptive materials capable of optimizing their own properties in response to environment replace static, energy-inefficient, externally regulated analogs. Our reversibly responsive material that controls light at exceptionally small intensities is yet another demonstration of this promising technological revolution.